Okay, for example 2, the probability density function for waiting times. Phenomena such as waiting times and equipment failure times are commonly modeled by exponentially decreasing probability density functions. We want to be able to find the exact form of such a function. We want to be able to think of a random variable as being the time you wait on hold before an agent of a company you're telephoning answers your call. So instead of x, we're going to use t to represent time in minutes. If f is the probability density function and you call at time t is equal to 0, then from definition 1, if it's going from t equals 0 to 2 minutes, of that function dt represents the probability that an agent answers within the first 2 minutes. And going from 4 to 5 of that function is the probability that your call is answered during the 5th minute. It's clear that f of t is equal to 0 for t is less than 0 because the agent can't answer before you place the call. For t is greater than 0, we are told to use an exponentially decreasing function. That is, a function of the form f of t, which is equal to a times e to the negative ct, where a and c are positive constants. Thus we have this piecewise function. F of t is equal to 0 if t is less than 0, and f of t is equal to a times e to the negative ct if t is greater than or equal to 0. So we're going to use equation 2 to determine the value of a. So we know the value of 1 is equal to this integral that goes from negative infinity to positive infinity f of t dt. Now going back to that definition, we can split this up going from negative infinity to 0, f of t dt, plus going from 0 to infinity, f of t dt. Now this represents where t is less than 0. And that means that we know it's going to equal to 0 because the agent can't answer before you place the call. So this is going to be 0 plus this becomes this function where it's greater than or equal to 0 since it's going from 0 to infinity. So now we're going to replace this function with a e to the negative ct. And we're going to go from 0 to infinity of that function a times e to the negative ct dt. So what we're going to do is we're going to take the limit now as x approaches infinity and it goes from 0 to x of that function. Now we're going to take the antiderivative of that and then plug in the lower and upper limits. So the limit as x approaches infinity is equal to negative a over c e to the negative ct going from 0 to x, which then equals the limit as x approaches infinity of a over c times 1 minus e to the negative cx. And what that ends up equaling, it equals a over c. And this entire thing is equal to 1 from the beginning of our problem. So if we know it's equal to 1 and multiply both sides by c, then we can see that a is equal to c. So therefore, a divided by c equals 1, and so a is equal to c. Thus, every exponential density function has the form f of t is equal to 0 if t is less than 0, and f of t is equal to now, instead of a, it's going to be, we're going to substitute that for c times e to the negative ct if t is greater than or equal to 0. And so here's what a typical graph is shown in figure 2 as an exponential density function.